Good morning. My name is Alan Caldera. I'm a distinguished engineer with Yugabyte, and today I'd like to talk to you about performance. And basically, what we wanted to talk about today is our top tips and tricks to optimize speed in your mission critical applications. So one of my favorite sayings is speed costs money. How fast do you want to go? So the most obvious thing is when you're talking about improving performance is to throw money at a problem in terms of your infrastructure spend. But what we're exploring here today is the time invested in optimizing an application and database system. So there is no single magic bullet that fixes all problems, even though you would want it to be there. And the techniques discussed here are usually employed in depth by an iterative process. So, it will take some level of experimentation. And as we go along in the product, you may find that some techniques, may work fine in some versions, but we may improve the product so that they're not needed in subsequent versions. So our areas of focus today are data modeling, performance structures, and flags and session tunables. We could also dig into things like query hints, but I'm going to leave that for some of my colleagues to discuss in other sessions. So the first thing that I want to talk about data modeling is, the reason why I want to talk about data modeling is we actually find that most of our performance actually comes from how the data model is actually built. So what do I talk about data modeling? I'm talking about key structures, so choice of primary keys, secondary keys, what table spaces you have, what kind of, how many tablets you allocate. So I wanted to kind of take you through what we're talking about there. So as kind of a refresher, Yugabyte splits everything into tablets for each table, tablets or quote unquote shards. And so basically for every key, whether it be a primary or secondary key, we have two components of it. So typically there will be a sharding key or a hashing key that basically tells you which tablet am I going to place certain data in. And then I will have, quote unquote, a clustering key. Those of you familiar with Cassandra will recognize this as partitioning keys and clustering keys. And we use these both, we use these concepts in the storage engine to do all of our key organization for this distributed system. So generally what we're going to do is we're going to have highly, we're going to have our high cardinality columns, be a sharding key, and our lower cardinality or range sorted columns would be clustering key. So we want to define a primary key for each table. This is because that if you don't create a primary key, basically what we will do is basically hash on an artificial structure like the row ID, and basically there'll be no organization to how the records actually get placed across the system. So we really suggest that you have a primary key designated for every table that you create. This is because YSQL tables and YCQL tables, for that matter, are indexed, organized by the primary key. So the index itself is the table is basically the index itself because we are a key value store underneath. And ideally, the primary key is the quote unquote most commonly used index. Okay, so we wanted to try and do as many of our accesses as possible using the primary key. So ideally, each common query pattern can use an index for the primary key. So the index columns should cover as much of the where clause as possible. So a couple rules of thumb: columns with stricter restrictions, i.e. higher cardinality, should come earlier in the key. So primary, so in the case where we're doing a query pattern where B equals 1 and A is a range where we're saying A in 1 to N, that it's usually better to have the equality as your first column and the fan out as a clustering column. So for both primary and secondary index keys, we support two kinds of splitting. So the first is hash splitting. This is the default. So basically the first column in every key is defined to be the hash key, unless you actually explicitly use an ascending or descending designation on it. So in a normal index definition, if you're coming from another database system like Oracle or SQL Server or DB2 or MySQL, then we will basically assign the first key as being the hash key. This has mixed results sometimes, particularly since I found certain instances where the indexes will have things like Booleans and other very low cardinality values at the front of the index, and so this limits the number of tablets that the index can actually be spread across. So we'll also discuss what you can do with range splitting as well. So our first choice is hash splitting. So let's talk about some of the pros of hash splitting. So tables and indexes can be automatically pre-split. So this means that operations can scale immediately. Our competitors usually use the technique of starting things in a single region and then splitting from there. And so as they scale, they're having to split into more and more regions to get that scalability. But with us, we actually pre-allocate our splits so that you can actually start seeing the benefits of our scalability immediately. And so what are some of the trade-offs and concerns? So the hash key needs to be fully specified to compute the hash and identify the target tablet. So what does this mean? So this means that if I have a hash key, which is H1, H2, then ideally I should have both keys specified as equalities, i.e. H1 equals 1 and H2 equals 2, as opposed to having one or both of those being inequalities, which will cause my query to quote unquote fan out or go across multiple tablets. When I do that, we will always go across starting from the lowest tablet number, i.e. tablet 0, and go serially across the tablets. So we want to make sure, the goal here is we want to get down to a single tablet as quickly as possible to optimize performance. So the second thing is that we need to have enough unique values to ensure a good distribution. As I was saying earlier, if you have a very low cardinality column, then we're not going to be able to have enough values to create enough tablets. And so there we might have to have, you may have to say, okay, well, this is only going to go across a certain number of tablets. Let's take something like, gender or a Boolean value or the month of the year. There are very few values to use, so we want to be able to have something that spreads very, very well across. So rule of thumb, you want to have the count be at least an order of magnitude larger than the tablet count. So if I have 50 50 values, then that only really gives me 5. That may give me something on the order of 5 tablets, but I want to have it works better when you actually have something like 500 or 5,000 values. Our second choice is range splitting. So the pros on this is it's actually more compatible with the existing Postgres semantics, because Postgres is a single node database, and so it expects to be able to split on ranges of values. And it can also handle things like inequality, so between queries, greater than, less than, greater than or equal to, and also sorting conditions. So some of the trade-offs with this one are it's very difficult to pre-split when you do range splitting. We do allow you to use what's called the split at values clause, but basically you have to know what the actual values are before you actually specify them. It can also be susceptible to hot shards. In other words, you could get a certain range of values, maybe always hit. So you may find yourself always going to 1 or 2 shards when you really want it to go to as many different shards as possible. And the last thing is part of the key is still really needed to identify the right tablet or set of tablets. So if I have multiple multiple values and I have multiple split points, I want to be able to basically be able to determine which tablet to actually go against, as opposed to having to fan out again. So one of our tricks is we generally tell people to change their primary keys to from a synthetic key, i.e. something that is generated by an identity or serial or other sequence type column, to a natural key. Let's say that I had the following table. So create table users, user ID, big int, not null, primary key, email address, name, etc. And then typically what we'll see is we'll have a unique index on the users table. For the sake of argument, let's say that I also have a foreign key on that user ID to other tables. This is a very common pattern. So if 90% of my queries actually use the email address as the key, then I actually have to do 2 RPCs for each query. One to actually get the index value to find out what the primary key, i.e. what the serial column actually is, and then another one to actually get the remaining data columns. So what we actually have people do is to save this additional RPC, without actually changing the application, is we say, okay, well, instead of making the user ID the primary key, you make the email address the primary key, because most of your queries are going against it. This way, when I query on email address, I'm actually be able to retrieve all the remainder of the attributes. And then I can use a unique index on the actual user ID. I can still continue to use a sequence or a GUID or whatever to keep that unique value and to use a foreign key against it. But this makes a huge savings when you talk about thousands, hundreds of thousands, and millions of queries per second going against this. It adds up. One of the next tricks we talk about in data modeling is we want to look at using less reference columns into JSON-B structures. Now, when you're migrating applications, from one database system to another, sometimes you have the flexibility to actually do some rework. And so in this case, what we tell people is, try grouping some of your less often used columns in JSON-B structures. This has a couple effects. One thing is that each column, we have to remember that each column is actually a separate write into DocDB. So when you have more columns, if you have tens, hundreds, or thousands of columns, you get more writes for each one, because each one of those columns is a separate key value entry in the storage engine. So this is less true when starting in 2.15 with packed rows, and I'll talk about that in a future slide, but this is still a useful technique. The other thing is that JSON-B columns attributes can be actually indexed, so you don't lose the flexibility in creating indexes on these columns. And it also allows for a degree of flexibility during schema evolution. How many of us have actually had to face the problems associated with syncing up application changes and databases, but when we have to add columns, if you have a JSON-B structure in there, you simply just have your application start writing the new column, and you don't have to worry about actually evolving the schema on the database itself. And finally, JSON-B columns can actually be included in covering indexes, which we will discuss a little bit later. The next tip is, talking about using the right number of tablets for each table. So if the table is less than 1 million rows and it is a low velocity table, i.e. you're not doing a lot of inserts, updates, and deletes to it, go ahead and place it either in its own tablet or in a co-located table space, i.e. you basically want to say create table, split it into one tablet, because it's really not useful to split, such a small table into many different tablets. As the velocity increases, let's say that this table is like some kind of job queue table or something like that, then we want to actually consider using the next technique, which is actually to use one tablet per node. So this again, talks about not wanting to create hot shards or hot nodes. So basically, we start spreading out this table across multiple nodes. So when you have the higher velocity of transactions going into it, then it has more places to write it. And finally, as we grow over 10 million rows into hundreds of millions and even billions of rows, the idea is to allocate multiple tablets per node across multiple devices. So basically, we start thinking about our best rule of thumb is typically we try to have about 6 to 8 tablets per device, and then but you can certainly have less. But if you need to have more, then you can start thinking about having more actual mount points, and that will basically allow you to scale it better. Finally, a couple of things to avoid and be cautious about. Even though I used an example earlier of using a sequence or a serial column, if you must use them for backward compatibility or application integrity, make sure that you alter the sequence to have a certain number of cache values. And so you want to basically pick the number, you want to cache the number of values that you expect to use, say, over a minute, as opposed to over a second, because each time you go back to where the sequence is stored, it actually is stored on the T servers now. You actually want it to you don't want it to keep going back to that tablet every time to basically fetch the next value. So please use a GUID or UUID where possible. The last thing is that if you are placing indexes on date and timestamp columns, do not make those columns the hash key. Typically, those columns are best left as ascending or descending range keys. But if you must use a date or timestamp column as a hash key, as the first key of an index, then use range sharding instead. So the way typically I see a lot of patterns where you have like last modified date or create date, and so people will have indexes based on those timestamp fields. So in those cases, you will basically want to explicitly call out ascending or descending on that. Now that does place it in a single tablet, but you will find that you're able to do scans a lot more efficiently. The next tip is we want to manage our cluster configuration with tablespaces. And so there's a couple of things that come around with tablespaces. The first thing is we're able to control leader affinity. Those of you familiar with Yugabyte are familiar with being able to pin leaders to a particular zone or region. Well, we can actually control this now down at the tablespace level as well. So this basically allows us to be able to pin data in certain locations, especially when we're using geo-partitioning. So in cases where we have clusters that are more isosceles shaped, i.e. you have two very close regions and one very far region, then we want to actually have the two close regions be able to say, okay, well, if I'm up, then that's fine. Otherwise, if I'm down, then I want you to go to the second, the second cluster over here that's close to me, as opposed to choosing one of the others. So an example of that would be we could create a table space where we can actually show what the actual leader preference is in the table space. So you say, okay, my first preference is US West 2, my second preference is US West 1, and finally US East 1 if all of those fail. The other technique that we want to do is we want to actually have cases where we especially when we're talking about a regional stretch cluster, we want to use geo-partitioning. We want to basically use the concept of a Postgres partition to put data that belongs, say, to Americas versus Asia versus Europe in actual different locations, not only to comply with local data residency laws, but just to also be able to have quicker access to the data. So the next thing I'd like to talk about are performance structures. So what do I mean by performance structures? So performance structures, typically I refer to as indexes. And so what we're going to talk about is techniques that we can use with indexes to improve performance. So the first one is we want to use covering indexes to reduce the number of fetches on the base table. So we use the include syntax to add regular non-key columns to a secondary index. So basically, if the index contains all of the selected columns, it can actually skip the table lookup, okay? So this means that if I'm selecting, say, a handful of values every time I go to a specific index, then I might as well go ahead and put those as include values, so that when you actually retrieve that, then you can actually say, okay, I've got it. And so therefore, I've done what's called an index-only scan. And so this reduces the number of RPCs, but the trade-off is that we do need to update the index when either the index or the included columns are modified. The next trick that we're going to talk about is using partial indexes. So partial index basically is where you can put a where clause on a create index statement. So basically, we're restricting the index to a subset of the rows. I've seen many applications that use Boolean values that say, okay, well, is this field active or is this field not active? And so, or is this field not null or is it null? And so those kinds of things can be encoded in the actual index so that, if you're not really interested in the other state, you can actually say, okay, I'm really not interested if this value is actually null. So I can say, create this table and then say create a secondary index where a specific column is not null. And so basically it will stop, it won't write, in that case, it will not write the index to the index for that particular value. So that saves you the write and a little bit of latency, and it also ends up reducing the amount of space taken, because we all know with databases, if you give it less work to do, it usually performs faster. Finally, another trick is to actually combine these two techniques to actually say, okay, well, given the table space discussion earlier, we can actually use the fact that we can create duplicate indexes in different geographies to ensure that we read from the local from a local copy that are actually strongly consistent, i.e. they get updated when the rest of the table does. So typically we do this with small reference data type tables, and there is a marginal uplift in the write latency for each additional index. So this is why we typically do it on the smaller reference type tables. And the other thing to keep in mind is that index-only tables are limited to 32 columns total, and this is a Postgres limitation, not necessarily one that we have. It's just something we inherited from Postgres. So this is where the technique of using JSONs also helps you, is you can include that as a whole column and pack a bunch of rows, a whole bunch of attributes into that. Finally, I'd like to talk about some flags and some session tunables. So the first one I want to talk about is this new session tunable called YB enable expression pushdown. So basically, in prior versions of Yugabyte, basically we would only consider things that were columns that were actually indexed. We'd get the index conditions pushed down to .db and then retrieve and then do the filtering afterwards when it came back. So with expression push down, we can actually go ahead and push down these other conditions so that when we send these reads to the remote nodes, we can actually filter those on the remote nodes before they come back. So this helps reduce the amount of processing that's coming back to quote unquote the proxy node, which is the node where your connection is. So this can be enabled at the session level by saying set YB enable expression push down to on, and it also can be enabled universe wide. The reason why it is not enabled by default yet is because not, due to rolling upgrades and things like that, we typically leave these kinds of features off until all of the nodes have been upgraded to where the feature actually exists. The next thing I want to talk about is follower reads. So we have 3 copies out there if we're doing RF3, and 5 copies if we're doing RF5. So basically what we want to be able to do is we want to be able to use the concept of follower reads, i.e., even though the data is not the current value on a particular node, I want to be able to read the value because it may be slowly changing, and I accept the fact that it might be slightly stale. And we're talking about, and we can control how stale that read can actually be. So in this case, if I've spread all of my leaders across US East, US West, and US Central, and I'm running the application in all 3 areas, then basically what I can say is, okay, well, if I can use this reference table from from a follower copy, then I know that it's slowly changing, and I can accept the fact that it'll get updated later. So this is also useful in cases where you have batch updates as well. So how do we actually use this particular feature? So we use this session tunable called YB read from followers. This is akin to using consistency local 1 in Cassandra. So this allows rows to be read from the local fault domain, even if it is not the leader. It must be used in conjunction with read-only transactions. And so the read-only transactions can be specified by a hint. It can be done at the session level. You can say begin read-only transaction, or it can actually be annotated in Hibernate Spring with an actual application annotation. So if you have the flag set, but if you do not have it in read-only transaction, then basically the reads are always going to go to the leader because we always default to strong consistency. And so we can also control the staleness of the data by setting the YB follower read staleness milliseconds. So basically we can say, okay, well, if it's 100 milliseconds stale, fine. If it's 10 seconds stale, fine. And this will basically allow us to you can control this at the application level. The next flag I want to talk about is a new feature called packed rows. I alluded to this earlier. This new G flag, YSQL enable packed row equals true. This is available in version 2.15 and later. Traditionally, our rows have been stored as K1C1, K2, K1C2, K1CN with the associated hybrid time. So each one of those would be a separate write, as I discussed earlier. Our new format, when you enable packed rows, is basically we write a key and then all of the associated columns with it. So this allows you to reduce space amplification, as well as it reduces latency on reads and writes, because when I write, I'm writing only one row into the key value store, and when I read, it's the same thing. Okay. And then when updates happen, we will still write those as individual updates, unless all of the non-key columns are updated in the update statement, and then we'll do it in a packed row. And then finally, compaction will actually remerge all the updates done to the non-key columns such that they are in the packed row format. So there's no migration needs to be done here. You turn the flag on, and basically it will start writing in the new format immediately. And as compactions occur, it will move the older data into this format. So in summary, performance tuning is an iterative process and an art. It requires the investment of time and willingness to think in terms of the distributed model. Future enhancements may obviate some of these techniques, and these are the most common tricks that have yielded the highest returns. So this is not by any means an exhaustive list. And finally, as a closing announcement, I'd like to give a shout out to my colleague, Frank Pachot, who's doing a more in-depth SQL tuning workshop at the time listed below. For those of you that may miss it, please go ahead and see his recording. Have a good day, and thank you for attending.